I've been talking about how we use the sine and cosine functions in simple harmonic motion and also in Faraday's law. And I would use more of it in the coming videos on alternating current. So it would be good at this stage to quickly review the kind of formula and behavior of sine and cosines. So in the topics on simple harmonic motion and Faraday's law, I've sketched some graphs of sine and cosine functions. So let me try to draw this here. A sine function would look like this, and a cosine function, right, now I want to make them match so we can clearly see the connection. The cosine function will start from a maximum, and it would look like this. Okay, and suppose that is x and that is y, that's 0. Then this one would be y is equal to sine x, and this graph would be y is equal to cosine x. Okay. Now we should look at these two and understand the connection between them. From the graph alone, you can see that the cosine graph looks just like the sine graph, except that the cosine graph is shifted to the right by 90 degrees. So in radians, that would be, let's see, so that's the peak of the sine function, and that's the peak of the cosine function down here. So that point is the 90 degree position, or in radians is pi over 4, not pi over 2. That's the 90 degree position. So this relation can be written in this way. We can say that cosine, well, we can represent a shifted graph by taking say sine x. If sine x is shifted by 90 degrees to the right, we can represent that as sine of x minus 90 degrees, minus pi over 2 radians. So if I plot the graph of this, it would be the graph of sine x shifted by 90 degrees to the right, which is exactly the cosine graph. So therefore, sine of this is really equal to cosine x. Now physically, if you think about these two, we would often think that they are physically the same, because they are the same when you just move one of the graph. Okay, and especially if you're talking about say a displacement time graph, when x is the time axis right? When x is the time axis, it's just like, then it would be like instead of starting the timing at this point, I just start timing the oscillation a bit later, and then I would get this graph instead. So that's why physically we would often think that the two graphs are the same, and that's why in simple harmonic motion and in alternating current, we would often see formulas written like this. Like for simple harmonic motion, you might see a formula for the displacement x written as x naught sine omega t, and for the say alternating current, you might see the voltage. That's for alternating current. You might see the voltage written as V naught times sine omega t. And this doesn't mean that the voltage has to be sine and cannot be cosine. Okay, what it means is it's just a general way of representing the idea, in the sense that if you plot the graph of this for the voltage or for the displacement, it would look like a sine graph, but the understanding is that it is just one example, and that the function would be different if I start timing the graph or the motion or the voltage at a different time. Like if I were to time it in a quarter of a cycle later, right? Then instead I could have maybe I could have x equals to x naught cosine omega t, or I could have v equals to v naught cosine omega t. Right? It could look like that if I start timing a quarter of a cycle later, or if I start timing at any arbitrary point in time, it can just start. The graph could just start from any point along the curve. And if I do that, then I might imagine shifting this by a certain time, say t naught. Yeah, if I time at a different time, t naught, maybe let's say I start timing say there instead. Let's say that time there, and let's say that's t naught. So instead of x, think of this as maybe instead of making it too complicated, I'll just leave it. So if I start timing from another point, say t naught, then my function would look like this. Maybe x naught sine. So instead of omega t, I have omega times say t minus t naught. So that's if I start timing at this time t naught. Or my alternating voltage could look like this. Omega times t minus t naught. Right, so we must remember, if you see this formula, V naught sine omega t, it depends on the question, sometimes or the situation. Sometimes for a particular example, this might be the actual voltage that is given. But sometimes in discussions or of general ideas, the sine omega t could just mean an example, and that it is always possible for the voltage or displacement to be a cosine or some function like this. Now the next thing about sine and cosine that we might use is a formula is the formula for the gradients of this graph. Now, as we have seen for both simple harmonic motion and for Faraday's law for AC generator, we need to know the gradients of the function. Now, if you have learned calculus, you know that when you find the gradient by taking d by dx, If you differentiate, if you do d by dx of sine x, you will get cosine x. And if you do d by dx of cosine x, you will get minus of sine x. So the d by dx is really just the gradient. Now, if I have this formula instead, if I have omega t in the formula instead of x, and I want to find the gradient with respect to time, so that means that I have sine omega t, and I want to do d by dt instead, then I would also get sine omega, I will get cosine omega t, but I must use the chain rule to also differentiate the arguments with respect to time. So that means that I would get a factor of omega outside. Okay, and if I do d by dt of cosine omega t, I would get a minus sign, minus of sine omega t, and again using the chain rule, I will get an additional factor of omega. Okay, and actually that is why if we look at the previous videos where I explain how to get the velocity for simple harmonic motion or the induced voltage for the AC generator, the resulting formula has the factor of omega. So let me write this out here again. Right, so in the example on simple harmonic motion, let me start with that. For the simple harmonic motion, I have talked about how, starting with the displacement, okay, the displacement is given by the sine function like this, so that x is equal to x naught sine omega t. Then we know that the velocity is given by the gradient of this. So the gradients I've written it as v is equal to the change in x over the time taken. Now for very small time intervals, that is written mathematically as dx by dt. Right, and in calculus, this is how we would calculate the answer if x is sine omega t. So therefore, using this formula, okay, I can calculate the answer for this, for the gradient. So the gradient of sine omega t should be omega cosine omega t. And there would be this additional factor of x naught for this example. So these two are fixed values that don't change with time. So if you now sketch a graph of the velocity, it would look like a cosine curve. This is what you get. So that's how we would get this formula from the displacement in a simple harmonic motion. Now let's look at the case where we have the changing magnetic flux in a coil. So let's sketch the graph again. Now about 2 videos ago, I talked about how if you have a rotating coil, the magnetic flux linking the coil would follow a cosine curve. Remember that whether it's sine or cosine, it's physically the same. It just depends. It's just a matter of where we start timing the flux. And this was given by, let's see, flux was given by the magnetic field flux density times the area of the coil times cosine of the angle between the magnetic field and the normal to the area. So that's cosine omega t. Right, and to find the induced voltage, we need to use Faraday's law. So according to Faraday's law, the voltage is equal to, this time we understand the minus sign from the last video, so I'll put that in. The change in flux divided by the time taken. And for very, very short time intervals, we know from calculus that this is d phi by dt. So this is the gradient of this graph. Okay, and now that we are going to use this formula, we know that when you do d by dt of cosine omega t, this is what you get, and that's what we need to do to this function here, ba times cosine omega t. So if you differentiate the cosine omega, this is what we get. Let me write this down. So minus omega sine omega t with the factors of b and a. Okay, but there's a minus sign here, so minus become a plus. So this then is a sine function, and I can now sketch my induced voltage graph. It's just a sine function. Okay, and we can understand why now that there is this additional factor of omega, which physically means that if the coil rotates faster, that means it has a bigger angular velocity, we would expect to have a bigger voltage. And that makes sense from Faraday's law, because a faster rotation means that the flux changes, the flux changes at a bigger rate, right? The flux changes more quickly. So that's why the induced voltage is also bigger.